right. So, in the previous module we have seen how the dynamics of the fastest possible process breaking of a bond was determined in Ahmed-Soel's group, and we have also seen how they could show you, not only give you a time constant, but actually tell you how the process is taking place, making and breaking on and on until it breaks and goes away. Now, what we will do is we will jump cut to a couple of decades later and present to you the glimpses of a couple of pieces of work from Eric Nebering's group in Max Born Institute, and this is my favorite. I like it very much. One reason is that I read it in real time the moment they were published, and also Nebering had come and I heard him present this work. So, this is elegant. So, what has been done is this. Okay, all of us have studied acid base reactions in school and college, right? And what is written invariably in chemistry textbooks is that acid base reaction is very fast and the mechanism is unknown. Mechanism cannot be established because it is so fast, right. Now, what we are going to discuss in the next 10-15 minutes is how the mechanism of this supposedly impossible to establish mechanism kind of reaction, how then that mechanism was elucidated by pump probe spectroscopy. Once again, I will not discuss the whole story, I will just present to you the logic, and then you should read these two science papers. Once you know a little bit about pump probe spectroscopy, those papers are not very difficult to understand. All right. So, what it did is, again in the beginning of the course we had presented the concept of photoacidity. We had said that organic acids become stronger acids when they are excited, organic bases become stronger base, and we had explained why in the light of molecular orbital theory. So, what Nebering's group did is that they used a strong photoacid pyranine or HPTS as it is called. So, here you see and they used OD. OD signal is easier to see in this experiment, and they used a regular base, that is acetate ion. And the idea is that they would excite pyranine, it would lose D plus ion to form the what they call the photo base, and this acetate ion would get deuterated to give you deuterated acetic acid. Okay. This is the reaction, and how do you follow it? By using pump probe spectroscopy, but here the pump is visible 400 nanometer or something, because that is where pyranine absorbs anyway. The probe is IR, probe is not your visible, because the good thing is if you use IR, there is a lot of data, do not look at everything, just show at wherever the arrow points, just see wherever the arrow points. This here is the IR spectrum of acetic acid, and it is a little different from the IR spectrum we are used to see, because y axis is absorbance and not transmittance. So, the idea is this is your acetic acid absorption in IR, of course that OD will come, deuterated acetic acid, and this is the absorptions of the photobase and photoacid. Remember what photobase and photoacid is? Photoacid is pyranine, deuterated pyranine, photobase is the deuterium removed, right, the anion, corresponding anion of pyranine. And these are the IR spectra of those. Now, the idea is, but to start with the ground state, what do you have? You have the photoacid and you have no acetic acid. So, when you excite by an ultrafast pulse, if you use the frequency of characteristic absorption frequency of deuterated acetic acid, then you should see a transient absorption signal, right. Point to note is that this transient absorption signal arises due to absorption of a ground state, not an excited state. Okay. And techniques like this are often used in other experiments, like recombination of axial ligands of heme proteins. So, transient absorption does not necessarily have to be of an excited state. Okay. It is forming as a result of excitation of the photoacid, that is right, but what you are looking at is the ground state absorption spectrum of acetic acid. And this is actually the most useful range of frequencies, as you see that the transient absorption spectrum changed significantly. You can also work with this range, and Neighboring group has actually done that, but there is significant overlap between the absorptions of photoacid and photobase. So, you might understand that analysis of this part of the transient absorption signal is a little more complicated. Read the paper, they have actually done it, but this is very easy to follow. So, what you should see in the second panel is how the absorption of acetic acid changes as a function of time post excitation of pyranine photoacid. Okay. Is the problem understood? What do you expect to see? You expect to see a rise time? Yeah. So, they looked at the rise time, and what they saw is that first of all rise time is there. Secondly, you see a smaller rise time if you increase the concentration of acetate ion. Why? Because if you have a higher concentration of acetate ion, then the moment this deuterium ion is liberated, I do not know whether it is a good idea to use words like moment when you are talking about ultrafast phenomena, but I think you understand what I am trying to say. When the D plus ion is liberated as a result of photoexcitation of pyranine, it finds an acetate ion faster, that is what I mean, if the concentration is more. That is why the rise time is shorter as you increase the CH3CO minus concentration. And also they compared the evolution, time evolution of the signals for photobase and CH3COH. So, at high CH3CO minus concentration, you can see the dynamics are more or less the same. See, photobase is also produced as a result of excitation, right, because you start with the photoacid. When the D plus goes out from pyranine, two things are produced. First is photobase is produced right away, and then that liberated D plus is taken up by acetate ion, and then acetic acid is produced. The question is, are the dynamics same for these two processes? The rise in the population of photobase and rise in the population of acetic acid, are they same or different? What do you expect? If it is a simple mechanism involving something like this, where you have contact ion pairs HOD and B minus, then when D plus is liberated, what do you get? Well, ROD. So, you get RO minus and you get DB, let us say. So, dynamics of formation of RO minus and dynamics of formation of DB should be the same. Understand what I am saying? So, rise in population of the anion of pyranine and rise in population of acetic acid should be the same if they are just two ions in contact and it happens instantly. That is what you get for high concentration of acetate ion. However, when you work at low concentration of acetate ion, this is what happens. This is the dynamics of photobase and this is the dynamics of your acetic acid. Actually, I should have written CH3COD here because it is D plus. So, which one is first of all they are not the same. Which one is faster, which one is slower? Formation of photobase is faster, right, and formation of acetic acid is slower. What does that mean? It takes some time for D plus to get liberated, right, and time taken for that is reflected in the time taken for population of the photobase to build. Okay. After that, if the proton is doing something else, gets engaged somewhere else, then the time of formation of acetic acid will be longer. Understand what I am saying? Yeah. So, I pass on a message to you. If I speak to you, the time taken for me to get rid of the message and the time taken for you to get the message is the same. But suppose I do not tell you, I tell somebody else, that person tells somebody else, that person tells somebody else, then I have delivered the message, but some time would go before you get it. That is what is reflected in this kind of a difference in population dynamics of the photobase and CST-CoH. Okay. And then of course, this is a very qualitative way of putting it, but it is very important because it gives you the idea. The idea you get is that at high CST-CO minus concentration, this is the situation. At low CST-CO minus concentration, when you have a chain of solvents in between the proton donor and proton acceptor, then it takes a little longer. Okay. This is the qualitative picture. To get the quantitative picture, what they had to, and that is why they got not one but two science papers out of this. They did a thorough analysis of the data and established quantitatively how much time it takes for the proton to get lost from the photoacid, how much time it takes for it to get associated with water, and then after a thorough analysis they came up with this picture. Looks very simple when you look at it, right, and in fact looks almost intuitive. So, what they said is ROD plus B minus. First there is a diffusion stage. In diffusion stage you have a lot of water molecules, they are separated. So, they come a little closer and they have this, you can call it water polymer between the proton donor and the proton acceptor. This is called the encounter stage, where this polymer is eliminated and you form the contact ion pair, and then you have the reaction stage where the proton actually gets transferred. So, what you see in front of your eyes is the reaction mechanism of acid base reaction, something that has been believed for a long time to be beyond our capabilities. So, for the last 13-14 years this has not been beyond our capabilities. We know exactly what the mechanism is, and what is not written here is that you see all these rate constants, all the values of these rate constants are exactly known. Okay. That is the power of ultrafast spectroscopy. Not only do you get to know how a bond is broken, you also get to unravel mechanisms of reactions that no other technique can. Okay. So, this is a fantastic piece of work from relatively recent times. After all, we have been showing you papers from 1972, 1965 and so on and so forth, which is still recent compared to what we usually do in classrooms. In classrooms, we often talk about things that were already known by 1900, but what you see now is the paper was published in 2005 in Science, fairly recent. I hope to get back to the work of Nievering once again when we talk about energy transfer between vibrational modes of water. But before that, let me see if we can introduce another excited state process, which is perhaps the most widely debated excited state process of all times, and that goes by the name of twisted intramolecular charge transfer. And there have been bitter fights over decades over whether that first T in TICT should be there or not be there. Okay. So, to cut a long story short, and I will show you the example. Suppose you have a coplanar molecule in which you have this donor moiety and the acceptor moiety, right. They are bonded to each other and they are coplanar. Coplanarity is essential, or at least so it was thought, because when they are coplanar, two rings, then their pi electrons talk to each other, right. If they are perpendicular, then that communication is lost. So, the idea was that you have this donor and acceptor coplanar, excite by light, then the electron transfer takes place, and then that if that is associated with a twist, then what will happen? You have deep delta minus on one side, delta plus on one side, and since these delta plus and delta minus fragments are perpendicular to each other, that electronic communication is lost. So, you cannot have back electron transfer. The reason why interest grew in this kind of systems was because people wanted to develop things like dye-sensitized solar cell. What is the meaning of a battery or a cell? If you have a plus end and a minus end, right, essentially that is what makes a cell. So, here the idea was that light energy would be converted potentially into electrical energy, because you are producing a molecule, one end of which is plus, one end of which is minus. Now, how you are going to connect the two ends of the molecule, that is a different issue altogether. In any case, we are not going there. But then what it, as it turned out, that more than making a solar cell out of this, a very rich field of photophysics was unraveled by this kind of molecules. The most celebrated perhaps molecule of this class goes by the name DMABN, dimethyl aminobenzonitrile. Even now people work on it. I do not know how many thousand papers have been published on the photophysics of DMABN and its brothers and sisters and cousins, but even now people find use for it. So, DMABN, you can see what the structure is, and for a chemist, if I say dimethyl aminobenzonitrile, that should be enough. You can see that you have this donor moiety and acceptor moiety, and the idea was that after charge transfer they become perpendicular to each other. The fact that charge transfer takes place is not very difficult to understand, because if you look at the fluorescence spectra, and here when you look at the fluorescence spectrum, be careful, this paper is not very recent. Well, I am showing you a 1992 paper, but that is sort of a review. This is after 2 decades of work. Okay. So, this data is not really from this paper, data is from some 1970s paper. So, they used to draw things differently at that time. As you can see, x axis is nu bar in centimeter inverse, I do not know if you can read, and this side is the high energy spectrum, high energy side, this is the low energy side. Is that right? Yes, it is. This is 16 on the left side, this is 24,000 or something, 16,000, 24,000. So, what you see is you have two kinds of bands, spectra are reported in several solvents, NXN is nonpolar, and there is only one band, the B band, so called B band, which is higher energy. And if you go all the way to acetonitrile, then you get only A band, a Stokes shifted band. And remember what we said, the Stokes shift is one of the signatures of excited state process happening. So, something is happening post excitation in this molecule, and it is charge transfer, because we will see why we think it is charge transfer. Right. What you see here is not exactly Lippert plot, but it is the maximum of spectrum, fluorescence spectrum, centimeter inverse, plotted against a polarity parameter. This polarity parameter is obtained from Lippert-Mataga equation, which we will talk about very briefly in the next module. So, what you see is this, look at absorption. This is the graph for change of absorption maximum in centimeter inverse with polarity, not much. This is the second one, is the variation of the emission maximum of the B band, the higher energy band, with change in polarity. Well, you do not see it in very highly polar solvents, or it is very feeble, but as long as you can see it, there is not much of a variation. But when you look at A emission, there is a distinct dependence on delta F. More delta F is a polarity parameter, greater value of delta F means the solvent is more polar. We will see what it is little later. So, for a more polar molecule, we see a greater red shift of the A band. What does it mean? That means the A band, the Stokes shifted band, is associated with a polar emissive state, right, and that corroborates nicely with this kind of a picture, that the higher energy state corresponds to this, where charge transfer has not taken place, lower energy excited state corresponds to this, where charge transfer has taken place. But why do you think there is a twist? In the data that we have shown so far, we might have been able to establish that the Stokes shifted band is associated with the polar excited state. Who has said that there is a twist? Lot of calculations said. First of all, we are not going to show you all that, but we will present another piece of work, extremely elegant piece of work, this time from Eisenthal's group, Columbia University, Department of Chemistry, Kenneth Eisenthal. So, what he said is this, that we think that it is associated with the twist from theory calculations and some other preliminary steady state fluorescence spectra. If there is a twist actually, then the photophysics would depend not only on the polarity, but also on the viscosity, because whenever there is segmental motion, that has to take place overcoming the viscosity of the medium. So, for more viscous mediums, the process would get slowed down. So, before this work in 1987, there was plenty of work of usual Lippert-Mataga plot and all that of DMABN. So, the reason why I am very fond of this work, and actually everybody should read this paper, Chemical Physics Letter. So, the paper is not very big and not very difficult to understand either. This is a must read paper for anyone who wants to work with photophysics of molecules, especially because it is extremely instructive. It teaches you tools in one paper that can be very useful if you are going to work with new molecules. So, the beauty of this work is that Eisenthal, and I certainly cannot remember the name of the then student who worked on this, they said that, well, what about viscosity dependence? If you want to talk about polarity dependence of the rate constant associated with this, then we should also take into account the role of viscosity that might be there. So, what they did is, they did two things. First experiment, result of which that you see here, is due to mixture of isoviscous polar and non-polar solvents at room temperature. So, what happens when you take mixture of isoviscous polar and non-polar solvent? Two pairs are shown here. One is C3H7Cn nitrile, and they actually did a series of nitriles, and octane. And the reason why they chose these two, as you can see, none of these are commonly used solvents, right? Whoever works with octane, whoever works with C3H7Cn of all things. But they chose this pair because this pair has the same viscosity, more or less same. But octane of course is non-polar, nitrile is polar. And another representative mixture is C4H9OH, butane and hexadecane. Again, you might think that sometimes we might have done experiments with butane, butanol, sorry, not butane, butanol, but hexadecane of all things. The reason why they were chosen once again is that they have same viscosity. And then the first solvent mixture is the mixture of a non-polar solvent and a polar aprotic solvent. Second one is a mixture of a non-polar solvent and a polar protic solvent. So, not only do you get to understand the role of polarity and viscosity, but also the role of proticity. So, and everything is done in room temperature. X axis is ET30. ET30 is an empirical micropolarity parameter introduced by Richard. Richard has a book on properties of solvents, where ET30 is discussed very nicely. Essentially, what Richard's group did was, they looked at, Reichard is what we often pronounce his name, but I think the correct pronunciation is Richard, but I am not good at German pronunciation anyway. So, they worked with a library of molecules which exhibit solvatochromism, and they found out that the absorption maximum of this betaine dye number 30, 30 is basically a roll number, right. When you work with a large library of molecules, Faryad here works with molecule 72 all the time. Who is going to mention the IUPAC name? All of us spend so much of time in school learning IUPAC name, we hardly ever use them, because we work with molecules that have IUPAC name. If you try to write it, it is not a name, it is like a name, address, a lot of things. Okay. So, absorption maximum of betaine dye number 30 in their inventory. Okay. If somebody else might have called it dye number 82, I do not know, but they called this dye number 30. and they worked with a series of betaine dyes, they found that their dye number 30 has this absorption maximum, which is nicely dependent on polarity. So, what they said is this, why do they call it micropolarity? They say that, see, organization of a solvent around a solute is very different from the organization of a bulk solvent, especially for polar solvents and polar solutes. So, the polarity that we measure by measuring dielectric constant need not necessarily be the polarity experienced by the solute. In fact, sometimes the polarity is much lower, right. Around a solute, polarity of water, epsilon of water is about 5, whereas bulk polarity everybody knows, very high value. So, they said that when you talk about photophysics, when you talk about a property of a solvent, a solute, you should talk about not epsilon, not dielectric constant, but some kind of a polarity parameter that is seen by the solute. See, when you do spectroscopy, you use fluorescent probes or something, they are very myopic, they do not see very far away, they see the first solvation shell, maybe second solvation shell, beyond that nothing. So, they introduced this and they said that this is a better polarity parameter when you are talking about photophysics of solutes. So, that is what they used, and they found that when they plotted against ET30, you get this two different lines, one for the nitrile nonpolar solvent mixture, the other for your alcohol hexadecane mixture. Okay. Good thing about these plots is that there is no effect of viscosity in any of the plots. Okay. The plots are not the same, right. That could be because this mixture has a different viscosity than this mixture. It could also be because here we have protic solvent, here we do not, that we will elucidate later on. But then what is done here is that if you forget about viscosity, polarity dependence is clearly there. So, this is a superior piece of result than what I showed you a little earlier, simple Lippert plot, because viscosity is taken care of. Another way of handling situations like this is to do multiparametric analysis, what is called Cumlet-Taft analysis, that is also very useful in understanding complex situations.